SwayamPrabha. Digital India. Educated India.
Good morning. Let's continue our discussion on this finite element equations being developed for 2D solid mechanics and 3D solid mechanics. So we have formulated the potential energy, which is in this form, to the triangle, and where we found out the stiffness matrix, as well as this is the nodal load vector. So if we collect these things, so the potential energy phi of the body, we can for each element. So this is how it is over all the elements. So we are assuming that there are any number of elements, and so this is what we have just now simplified. So it is nothing but, so what we have here is that it's half UE transpose K so this is for one element, a generalized triangle, and so this is half UE transpose K times U. So this is what we found out, the strain energy, and together with this one, so we also have the work of external force, which we also have a similar expression, UE transpose so this is due to the external forces, and then this is the forces here, which is given by this one if it is the body forces. If it had been if there are fractions on some boundary, on fraction boundary gamma t, like here, so this is what we said, and if it is, then those things had to be included in the fraction, and then that also will come out as Fp, which will be on gamma t so this looks like similar to the body force contribution, and it will exactly follow the same thing. So I'll just if there is a triangle here, IJK, whose side JK falls on this one, then So triangle J side for example side JK falls on the attraction boundary. So without too much of simplification, we did this once before, and then this 0, 0 JK by 2 TX okay. So the first two are due to the shape functions at here in x and y directions, okay, so which turns out to be 0 on this side, and then J, it has a shape function here which is equal to 1 and goes to 0 at k, so that's why integration is skj by 2 tx sjk by 2 ty, that's a y component, and then sjk by 2 tx and sjk by 2 ty, and of course a multiplication of t, the thickness of the plate. This we are writing okay. So these are all the forces, and we also may include if there is a concentrated force, say at some point here, at some other node, say at K, if you have a concentrated force there, so that also need to be included, that concentrated force multiplied by the nodal displacement at that point because it's acting at the node. Okay, so those things may also have to be included. So that's those things can be taken care of. So now let's summarize everything here. So this may include this also, right? Okay. So now we have the total potential energy, which consists of this UE transpose K times U with half here, and then UE transpose times FE here. And so this is for each element. And then if you want to do it, so it will turn out to be, so the assembly, so as doing assembly, so the whole summation over all the elements this is all, so these are all, let me just put it as G here. So G is global in the sense that it will include all the elements. So here we have many elements, right? So because of that, so this will include all the things. So UG includes all nodal displacements, including like U1, V1, U2, V2, all the way up to UN, V1, the total number of nodes. So the total degrees of freedom are twice the number of nodes. Okay. So whereas this K here, Kg is a global stiffness matrix, which is an assembly of all these elemental matrices. And so similarly here, this U also, so this is also global and this is also global. So this is all global matrices. Okay. So how to assemble these things? How to get from elemental matrices to a global matrix? How to expand it? Because if you look at this one, now these are all matrices. So overall, it is a scalar just one quantity. Because if you just look at this one, this is 6 by 1, right? This is 6 by 6 and this is 1 by 6. So the multiplication of all these three quantities is just a 1 by 1. So that means that how do we assemble all these things so that you get a kg and these things. So now let's illustrate it. Illustrate it with just 3 degrees of freedom. 3 degrees of freedom. Let's take or 3 nodes for that matter. If you want, it is 3 nodes in 1D rod problem. Such as so let's just take 2 elements. Let's try to illustrate it with 2 nodes. 2 elements and okay, this 1, 2. So this would come out as the strain energy U here will be an assembly of these two. So how will it look like? So it is half will be there and it is U1, U2, A11, A12, so this is for the first element here. So for the first element, we have U1, U2, and this is the stiffness matrix and followed by again the displacement vector here in this way. So now this has to be added with another second element contribution, so which looks like U2, U3, A22, 23, 32. So these are all coming from element 1. This is coming from element 2. So this is how each element is contributing. So now let's how to combine this one, because each is a scalar, and how to combine them in a matrix form. Let's look at this one. So how we do it is that we will expand each one of them to consist of all the degrees of freedom, each one of them. So combining it, so there's a half here. Let's combine this so that you will have all the 3 degrees of freedom. Those are the global degrees of freedom. So here we'll have a 3 by 3, A11, 1, 2, right? A 2, 1, 2, 2. So this is coming from element 1. Okay, all superscripts 1 here. And the second element also will expand it as a 3 by 3 with the addition of U1 here. The second element doesn't have U1. And so the first row and first column are 0. Here you have A22, A23, A32, Okay, so this is the strain energy, right, of all the elements put together. So how do we combine this? So how we combine is that, so since these displacement vectors are exactly same in both the cases, so they can be taken out and so then if these two are exactly same for both the elements, so these two matrices can be added. Okay, so these two can be added. So it is K1 1 of 1, 1 2 of 1, 0, 2 1 of 1, 2 2 of 1, and we add 2 2 of 2 also here. Okay, 2 3 of 2. So this is how we add, right? This and this can be superposed. They can be added to each other exactly at the same location. So you can see here, interestingly, that the first element here is coming here and second element is coming here. So only at the node 2, so the two contributions are coming and then they are added here. Okay, this is nothing but an assembly procedure. So the first element, whenever you do the first element, immediately you can put it in the global thing. So exactly at the same location. So we know that these locations are 1 2, 1 2, right? And this is 2 3 and 2 3 here. So it will go to 1 2 1 2 and the other one will go to 2 3 2 3. Okay. So this way the assembly is done so that the displacement vectors now are a complete global displacement. So similarly, even the F also can be added. Okay. So similarly, F, so similarly, the F also will become global as we have here Fe1, Fe2, and this comes from element 1. So this here, the second component of this vector comes from both the elements, so they have to be added. So like this, so we can add and assemble it into a global thing. Okay, so the next is the most important part, is that the total potential energy is phi, which is now assembled so this is the energy, and so these are all global things. I put the subscript G here just to show that they are all global vectors, so which includes all the degrees of freedom. Okay, so now this is the potential energy, and now comes the minimum potential energy principle. What is the minimum potential energy principle? So here, this you can see here, this phi is a global potential energy, is a function of what? So this Kg here, the stiffness matrix, is a constant. Okay, so this is all constant. Given a system, geometry, material, and all that, Ke is constant and Kg also will be constant. So this Ug will consist of as many degrees of freedom as there are number of nodes multiplied by 2. So that means that this potential energy here is a function of this displacement, right? So this is the displacement. So that means that there will be as many displacements as the number of nodes multiplied by 2. So this potential energy is a function of this one. So what we need to do is that, so let us say this has consists of say U1, U2, n degrees of freedom. N is the total degrees of freedom. Total degrees of freedom. And I just wrote it as U1, U2, and Un. So please don't take them as x displacements only. So this will consist of both x displacement, y displacement, as well as z displacement also. So now this potential energy is a function of these things. If you change these things, the potential energy also changes. So what we need to do is that we have to minimize this potential energy using minimum potential energy principle. So what we say is that this dou p by say u1 is 0 and like this. So you can take a derivative of each of these displacements. So there will be n equations. So these are n equations. And you can also concisely write it. So the potential energy has to be differentiated with the vector u. So here we wrote u. In fact, you can put also g here. So this is what? This is a quadratic function here, half ug times k times ug here. This is a quadratic function. And then if you differentiate it, you will get a linear function. So u will appear only once. And here you have f only, and this will be equal to zeros as many, and so that is as many zeros as there are number of degrees of freedom. So this is which we can write it as k times the displacement, global displacement vector. So this is equal to fg. Okay. So this is the equation. The algebraic equation in terms of the unknown displacements, and these are the forces which we know, and k times u, all global, are appearing here. And then it looks like we can take the k to the right side by taking inverse. So ug will be k inverse fg. So this is a little written in terms of the matrices. So just for the sake of clarity, so let me just illustrate it with respect to the just a small 2 degrees of freedom thing, how we do it as an illustration. So let's of this procedure. of this procedure. So let's write it. So let's say in 2 degrees of freedom, say U1 and U2. So what we have here, then the potential energy looks like this: half U1, U2, and this is K11, 1, 2, K21, 2, 2. U1, U2, and so this is obviously a scalar because this is 1 by 2, 2 by 2, and 2 by 1 here. And this is 1 by 2 and 2 by 1. So this is all scalar. And so if you want to expand it, then you will have so this is K11, U1, K12, U2, K21, U1, F1. And further, so we will write it as K11, U1 square, K12, U1, U2, K21, U1, U2, K22. This is expansion of this one, minus F1, U1. Okay, so this is completely scalar, and this is the potential energy. Obviously, this pi, you can see that this is pi is in terms of U1, U2, a function of U1, U2, right? So now what we can do is that we can differentiate this one. So this is supposed to be to make pi minimum. Potential energy minimum. The conditions are, so we have pi differentiated with U1 is 0, and which will turn out to be, there's a 2 here, and so it is K11 U1 and K12 U2, K21 U2 with half there, K12 U2, right? And then here we have F1 equal to 0. So similarly, we have the second equation with respect to 2 will be, so there is nothing here, as K12 U1, right? And K21, or I'll write it here, U1 okay. So this is in the longhand, and we can combine them. It is K11, K12 plus K21 by 2 U1 U2 okay. So this is the second equation. So this is how you get it. So this is nothing but this is all coming from structural point of view, okay, using the Maxwell's principle. Maxwell's reciprocal principle. So where this is a symmetric matrix and 1, 2 is 2, 1. So either you can replace 1, 2 with 2, 1 or 2, 1 with 1. So it is K 1, 1, 1, 2, 2, 1, 2, 2, and U1. Okay, so this is exactly what we got it, what we put it for n degrees of freedom. Now I showed it for 2 degrees of freedom, how you can get it from starting from here and then going through expansion and then taking derivative with respect to each of this component. And this is what we get exactly. So it is K times the displacement vector is equal to the force vector. Okay. So this is how the variation principle. There are a few important factors also here, so which we will discuss tomorrow while discussing a problem. So tomorrow we'll take up a problem and then illustrate it completely with all numerical values. Okay then, bye. See you tomorrow.